Hey guys, I'm Pat Kelly. Okay, in this problem, they ask us to use mathematical induction to prove this property that's stated here. And in this case, they're stating that this expression, 2 raised to the 2n plus 1 power plus 1, is going to have a factor of 3. Okay? And with mathematical induction, you always have two main steps that you have to show in your work. So let's begin with step 1. And step 1, which you always want to be thinking, is that you have to show that this statement is true for the lowest n value that's involved. Okay? Typically starting at 1, and that's where they want us to start with that inequality. And then if we're going to show that this statement is true, you're going to grab that value of n, 1 in this case, and put it into this expression. Okay, so I'm looking at 2 raised to the 2 times 1, just putting a 1 in for n, plus 1, that's all up in the exponent there. And then after that, there's still a plus 1. Let's actually simplify that right away. That equals 2 times 1 is 2, plus 1 is 3. So we're looking at 2 raised to the 3 power plus 1. Let's simplify further. It's 2 to the 3 power is 8, plus 1 is 9. Looks good. But I'm going to keep going, and I'm going to rewrite 9 as 3 times 3. Okay? Because what we just showed then is that this original expression with a 1 being put in for n does have 3 as a factor. And I'm seeing that right there. You can actually pick whichever 3 you want, but when we say 3 is a factor of the expression, that means we have 3 times something. Okay? All right, which means step 1 for mathematical induction, show that it's true for your first case, your first value of n. That has been accomplished. Okay? All right, moving on. Second step you'll always want to include in mathematical induction actually has two parts itself. And the first part in the second step of mathematical induction starts with an assumption. You always want to assume the given statement, which is this guy up here, assume that that's true for the value of k. Okay, so we're going to assume 3 is a factor of, and I'm looking at this expression, but I'm just putting a k in place of n. 2k plus 1 in the exponent, and then plus 1. Okay? All right, let me slide over here for a second, because what I just wrote down in words, you're going to want to be able to see algebraically. It's going to serve you in a minute or two. Okay, so let me say comma, that is, in other words, what did I actually just say there in words? 3 is a factor of this expression. What that means algebraically is that this expression, 2 raised to the 2k plus 1, and then plus 1, equals 3 times something. I'm going to pick the letter J. You can really pick whatever letter you want. But the point is that 3 is a factor of this expression, because 3 times something will get you that expression. Okay? And I'm going to use that. So let's move down here, because I said that the second step of mathematical induction actually has two parts. The first part is always the assumption, and the next part is something that you want. And what we want is for that statement to be true for the next case, the k plus 1th case. Okay? So we want 3 to be a factor of, and I'm looking at this original expression again, but I'm going to put a k plus 1 in place of n. So I might even switch colors for that because I want to pick on it in a minute. 2 raised to the 2 parentheses k plus 1, close parentheses. There's still a plus 1 up in the exponent and another plus 1 down here. Okay, so we want 3 to be a factor of this expression. And I told you I picked a different color because I wanted to pick on it a little bit. I want to play with it a little bit. And really the play that I need to get into is a key part of this problem. And it's all just algebraic play. Maybe you'll have some fun too. But the algebra that I do, I'll warn you, will get a little bit tricky. I'll go slowly and try to explain what I'm doing. So I'm taking a look at this expression. Let me slide down here. I'm still in the I want mode. So even what I said here in blue is what I want. But I'm going to take a look at that expression that I wrote there in orange and play with a little bit. And the first play is just 2. And then we'll play with the exponent. You can just see some algebra distributing through parentheses. We'll get 2k. Let's do a little bit in our heads. This 2 distributes through, so you got plus 2, but then plus 1, so that's plus 3, right? And then there's still this plus 1 out of the exponent, plus 1. What I'm going to do further with my play is I'm going to break down this exponent a little bit differently, 2k plus 3. I'm going to rewrite as the base of 2 still, but then 2k plus 1 plus 2, all still in the exponent. I'll explain. And then there's a plus 1. And these algebra steps, I definitely want them to make sense to you. So always confirm it for yourself by thinking backwards. I mean, if I gave you this, you would agree with me that you could combine the 1 and the 2 and get this to 3, right? Okay, well, why? Why did you do that? This is key, very much key. Because what I'm trying to do is force something that looks somewhat familiar to me from my assumption. And my assumption is right here. There's an exponent of 2k plus 1 for the base of 2. So I wanted to force that. And I do still have a tag along here, but I'm going to address that in my next step. A little bit of algebraic trickery. Okay? So let me continue. And I don't want to muddy the waters here, so let me slide down here and continue. This equals. And what I'll do next is break this base of 2 with that kind of complicated exponent. I'm going to break it down and write it as 2 raised to the 2 power times 2 raised to the 2k plus 1 power. And then I don't want to forget about this plus 1 that's still there. And again, you might say, well, okay, wait a minute, what just happened? Always convince yourself it's legal and legitimate algebra by going backwards. If I gave you this guy, these are like bases, the 2's, so you could add exponents, right? Properties of exponents. So if you add those exponents, you get right back to the step above. All right, why did you do that? Here's the next thing. Now, I'm going to look at this 2 raised to the 2 power. Let's call it 4, right? I'm going to look at this 4 as a coefficient. So in my next step, I'm going to take this coefficient of 4 and break it apart into 3 of whatever this thing is that the coefficient's in front of. 2 raised to the 2k plus 1 plus 1 of them, 2 raised to the 2k plus 1. And then I don't want to forget that there's still this plus 1, plus 1. Again, take a breath, a little reality check. Go backwards. Let me grab even another color. If this expression here I gave to you as 3 times x plus, hey, look, that's another x. 3x plus 1x would give you 4 of those x's. That's why I called that a coefficient a minute ago. All right, what is your point? What are you doing? Why? That's the big question. And the why is important to you because you have to think this way in your own when you're doing your own problems. And the why is very much, again, trying to get back up to this assumption. Take a look at what I have right now with this assumption in square brackets, if you will. 2 raised to that power plus 1 is exactly right here. See it? Which means, we're almost done now, this is good. Which means that if this assumption's true, I can replace that square bracket with 3 times j. So this will equal, don't forget what's in front of it, the 3 times the 2 raised to the 2k plus 1, plus, now we're replacing the yellow square brackets with 3j. This is beautiful. If I go down one more step, we're there. It's beautiful because now you can factor out a 3 of the entire expression. See, there's a 3 here, and there's a 3 there. So 3 times 2 raised to that 2k plus 1 power plus j. The reason why that's so exciting for me is we have 3 times something. In other words, 3 is a factor of that thing we started with. So we got it. I'm sorry, I should point right here. This is what we wanted. We wanted 3 to be a factor of this guy that we started with. And we got there. Because 3 times something means that 3 is a factor. I did it. We got that to be true. So our second step, we got what we wanted. We're done. By mathematical induction, this original property is true for all values of n greater than or equal to 1. You deserve a pat on the back for that one, okay? Try some on your own. I know you'll do well.